Below is a special population of Sour Patch people. It consists of 3 different phenotypes: 9 blue, which is the sourest, 20 red, which is the sweetest, and 21 green, which is in the middle, all of which are represented by the genotypes shown above them. This population can be classified to be in Hardy-Weinberg equilibrium for 2 reasons. The first reason is that the population meets the 5 assumptions that come with the Hardy-Weinberg law, as seen below. The second reason is that according to the chi-square test, the B locus of this population is consistent with the Hardy-Weinberg proportions. We are able to find this chi-square statistic through the use of the allelic and genotypic frequencies. To find the allelic frequencies, you multiply the amount of homozygous genotype that has the desired allele by 2, add the number of heterozygous genotypes, and divide everything by the total number of genotypes multiplied by 2. These frequencies are represented by P and Q. To find the genotypic frequencies of the homozygous genotypes, you square either the P or Q value, depending on which homozygous genotype you want. To find the genotypic frequency of the heterozygous genotype, you multiply the P and Q value together and then multiply that value by 2. Unfortunately, this population of Sour Patch came into a very dangerous altercation with a very hungry college student. This student prefers the flavor of sweet rather than sour. By the student preferring to eat sweet over sour, it causes the fitness to improve as it moves towards the homozygous dominant genotype, the blue, most sour patch. This type of selection is called directional selection, or additive effects, since as you move in one direction towards a certain genotype, the fitness improves. To find their genotypic frequencies after selection, you take the initial frequencies of each genotype and multiply each by their respective fitness. This gives you the unadjusted survivors. However, the frequencies must always add up to 1 to represent the population as a whole. To make these frequencies add up to 1, we add these results up to get the sum of the row, 0.782. We then divide each of the unadjusted survival rates by this sum to get the genotypic frequency of the population after selection. We can now derive the allele frequencies after selection as well. You simply take whichever homozygous genotype frequency that has the desired allele and add that to half of the heterozygous genotype frequency to get the desired allelic frequency. This new population is not in Hardy-Weinberg equilibrium because this population experienced selection, causing the fitness across the population to be unequal. This violates the assumption of the Hardy-Weinberg law that states no selection can occur and that fitness must be equal across the population. After selection, the frequencies increase for the dominant B allele and for the genotypes with this allele since it promotes a flavor of sour. In comparison, the frequency decreases for the recessive B allele and for the homozygous genotype that has this allele since this promotes a flavor of sweetness. If this directional selection were to continue, the Sour Patch population would eventually only be made up of individuals with the homozygous dominant genotype that produces blue, sour individuals.